All right, hi everyone. I'm Andreea Buterchi. I'm the Vice President of Engineering at Veridise, and in today's talk I will present two security tools that we developed at Veridise for zero-knowledge proofs. All right. Perfect. Okay, so in the last few years we witnessed the emergence of ZK solutions, and here we're talking about privacy-based contracts, rollups, and even privacy-preserving blockchains. And actually, at Veridise, we audited several of these services, and our conclusion was that sometimes manually auditing ZK products might be challenging. So we wanted to push the limits of ZK security, and we started implementing tools that can automatically detect bugs and vulnerabilities in zero-knowledge proof circuits. And a few words about Veridise. We are a company that provides the traditional auditing for all the blockchain layers, but we are also developing state-of-the-art tools for securing the blockchain ecosystem in general. And we are doing that, so where we are providing access to these tools through our security as a service platform, which basically brings these security analysis tools to the fingertips of the blockchain community. And in today's talk, I will briefly discuss two of these ZK-related tools, which are PyCAS, an automated verifier for zero-knowledge proofs circuits, and ZK Vanguard, which is a static analysis tool. All right, so before I dive into the specifics of these tools, I will briefly tell you about the workflow of a zero-knowledge circuit. All right, so we start with the source code, right, which can be written in either Circum, Hello 2, or other domain-specific languages for zero-knowledge proofs. And this code is then transformed into a witness generator and a set of polynomial field equations. All right, and the latter is then converted into a prover and a verifier, which are collectively called a snark. All right, so one thing that I want to mention before moving forward is that unlike traditional programming, the source code contains both the computation and the constraints, and we'll have a look at that in a minute. Another mention is that for the examples in this presentation, we will use Circum. Cool, so a quick introduction to Circum. What you see here on this slide is a very simple example of a Circum template. So in the first part of this code snippet, you see the signals, input and output signals. And on the second part of this code snippet, you see the computations and also the constraints. And if you notice, like here we are using three operators: the assignment operator, the first one, the equality constraint operator, and the third operator, which is a combination of these two. So the third operator also affects the computation part and the constraints part. All right, so we can distinguish these two entities, the computation and the constraints, in this way. And usually how this works is the users provide the inputs, the computation part outputs a witness, which will then be used to produce the proofs. And after that, the set of constraints, the verifier which uses the set of constraints will say, okay, the proof looks okay to me, or no, the proof is invalid. And what we usually want is this computation part and the constraints part to be equivalent. And I will tell you why this is important. Perfect. So to formally describe this equivalence, it looks like this. This is a property that needs to hold. So basically, what this property says is that for every input-output of a program P, so this every input-output pair of P must satisfy C, the set of constraints, and for every pair that satisfies C, this pair has to be an input-output pair of P. And we realized that this property is often violated in, in zero-knowledge applications. And actually, this non-equivalence issue is the root cause of the unconstrained circuit. So basically, this is also related to non-determinism behavior. And in some cases, this non-determinism behavior produces multiple, distinct outputs for the same input, which is not desired, of course. And, in other words, this translates to the verifier could accept invalid computations. Awesome. And, these are just a few examples of the hacks in the wild that, were produced by violating that property I mentioned before, the equivalence property. All right, so let's have a look at an example. This is an intentionally buggy example. Basically, the issue is located in that for loop. What happens in here is that we don't loop up to n. We loop up to n-1, and the last. And if we instantiate like this example with n equals to 3, we realize that the last. So I didn't explain what this code does. So basically, it takes like a numerical value, and it will output its binary representation as an array of bits. And what is going on here when we instantiate this example with n equals to 3, we realize that the third output signal is unconstrained, and this means that the attacker can pass any value for this signal. All right, so there are some strategies that are usually used to find bugs or vulnerabilities in zero-knowledge proofs. And one of these strategies is static analysis. So how this works, it basically applies some predefined rules to reason about bug patterns in ZK circuits. And on the left corner, you will see an example. And for instance, for this example, since z, right, is a function of x, and y is a function of both x and z, the static analysis techniques could infer that y is uniquely determined by the input x, so it is unconstrained. It is constrained, basically. Another technique is SMT, and we can basically express this under constraint property as this logical formula here. And it is what this logical formula says that for every input that we provide to our witness generator, then we will always obtain the same output. So we don't have non-deterministic behavior. And for instance, if this property is satisfied, it means that our circuits are under constraint. So this is how SMTs find vulnerabilities. Of course, these strategies have pros and cons. For instance, static analysis is scalable, right? But it is not as precise as SMT is. However, even if it is more scalable, static analysis could provide false positives, and SMTs, even if they don't scale, they are the most precise in terms of security guarantees. So what we did at Veridise was to implement this tool called PyCus, which is a verifier that automatically checks whether a zero-knowledge proof circuit is under constraint. And what we did was to combine these two techniques that are, interactively communicate and share knowledge throughout the process of finding vulnerabilities in zero-knowledge proofs. So whenever the SMT gets stuck because it doesn't scale too well, static analysis could provide it with some help. So basically, here what we do is to combine the strength of both static analysis and SMTs, and the partial results from one phase to another can be used throughout this process. And at the end of this process, if PICUS will output true if it can prove that this set of circuits is properly constrained. It can also output false if it found a vulnerability in the constraint, and a question mark if it wasn't able to find anything relevant. And that's because, like PICUS also takes in a timeout. So when we reach the timeout and the tool doesn't find anything, then, it stops there. All right, so if you want to find out more about the tool, you can definitely check out our PLDA paper. We explain, we also share some results we obtained in the past, and you can check the paper by scanning this QR code. All right, so I prepared a demo of PICUS on our Security as a Service platform. So what you see here is the interface of our platform, and we basically upload the source code and select the circuits that we want to verify, and we submit. Basically here I selected the buggy version of this code, and we will see soon the non-buggy version of the tool analyzed to see what's the output of PICUS in that case. So here PICUS says that for input, for a specific input, we get two possible outputs, which is a warning that our circuits are non-deterministic. All right, so now we select the fixed version of it. And we will see that PICUS basically will say that it wasn't able to find anything wrong with the circuit. All right. So I would like to briefly talk about another tool, which is ZK Vanguard. So this is a static analyzer, and what you see on this slide is the general workflow of a static analyzer. So we start with the source code, which we compile and then represent it in a way that our analysis can reason about the circuits. And by taking in some detectors, we will output a report if we found or not something in the code. And this analysis representation is actually a constrained data flow graph, and I will explain shortly what this means. And of course, like ZK Vanguard has multiple detectors, but today we will focus only on the under constraint output. All right, so this is a simple example. Basically, this template adds two binary values, and the constraint part, you see like the second part of this example is the constraint part and the computation part. So the problem here is that we don't actually, our output signals are not constrained. Basically, there is no constraint on the input signals. So this leads to us being able to input bogus proofs, and the verifier will be able to, say that, okay, your proof looks fine, even if I inputted something wrong. So what is going on here is that, for instance, if we want to add 1 and 0, the output should be like basically 1. But if we set the proof to the carry 1, the result should be 3. So we basically are able to prove that 1 plus 0 is equal to 3. And the verifier accepts that because the constraint doesn't, refer the input signals. Okay, so this is how we represent in a visual way what is going on in that circuit part. The arrow lines mean that there is a relationship between the inputs and the outputs, and the dotted line means that the constraints between the input and output. And if our code is basically properly constrained, there should be dotted lines between all the inputs and outputs nodes in this graph, which is not happening here because we only constrain there are only equality checks for the output signals. Okay, so I also prepared a ZK Vanguard demo on SAS. It works similar to our PyCast tool. Basically, we have to upload the circum code. We select the path, the source path to the circuit. All right. Perfect. And now we select the under constraint outputs detector to see what Vanguard does, if it is able to detect something. All right, and Vanguard was able to detect that we have under constraint signals, and it mentions precisely which of the signals are under constraint. Okay, some takeaways. We all know that hidden ZK bugs could lead to severe financial consequences, and at Veridise, we try to mitigate these kind of situations by implementing automated tools that can automatically detect these vulnerabilities. And two of these tools are PyCast and Vanguard, which employ SMT reasoning and also static analysis to secure the ZK products. All right, so yeah, thank you very much for joining me. If you want to find out more about the audits that Veridise performed in the past for all of these ZK clients, you can scan the QR code and it will direct you to the page, the audits page on our website. Do you have questions? Thank you.
In practice, when you write a circuit, there are multiple constraints on the same piece of data.
Yes.
So you can only detect whether it's totally dangling. But if you're missing something crucial, when it's already slightly constrained, there's nothing you can do, right?
I don't think I follow your question.
I have a bit that is completely unconstrained, you can detect it. But if I have one constraint that touches that bit, you're already fine. But what if I need multiple? But because in the logic of the program, you need multiple constraints. There's nothing you can do, right?
Of course, we are reasoning about all the constraints that are part of the program, right? So if we find we try to reason also about the relationships between all these constraints, right? So for instance, an example is ZK Vanguard, which uses as an analysis representation this directed graph, and it tries to reason about the relationship between the input and output signals. So these kind of things could be in practice detected.
Thanks.
Okay.